Hello, so in this video we will talk about a concept called cut vertices and cut edges. So, but we start with the definition. Vertices whose removal along with their adjacent edges, if they result in a subgraph with more connected components than the original graph, they are called cut vertices. So this is also known as um, articulation point. Okay, and cut edges. uh, the same definition, whose removal result in a subgraph with more connected components than the original graph. The only difference is that for cut vertices we also remove the adjacent edges. For cut edges we only remove the edges. Okay, so they are also known as bridges. Okay, so before we go to the examples, we I want to highlight some observations. Now, in some texts, they are also known as they are also given as problems to prove, or show that if this is a cut vertex, this statement is true. Now, this is good. This is a good practice. But in terms of concept, what I want to say is that uh, think of it as an alternate definition of cut vertex and cut edges. So, for example, if a vertex that is an endpoint of a cut edge is a cut vertex if and only if its degree is not 1. Okay, so if you see a cut edge or if you see a bridge, then if you want to check whether the adjacent vertex is a cut vertex or not, you only check whether its degree is 1 or not. If its degree is not 1, then it is a cut vertex. If its degree is 1, then it is not a cut vertex. Okay, similarly, this statement says a simple graph that has two or more vertices must have at least two vertices that are not cut vertices. Okay, so in other words, if there's a simple graph which has three vertices, then there should be maximum one cut vertex. Okay, so in other words, at least two of them should not be cut vertices. So if we have a simple graph with n vertices, so this means that this, if I call it a star here, so if we have n vertices in a simple graph, then we should always have less than or equal to n minus 2 cut vertices. Okay, so this is another thing which what we need to keep in mind. Then again, an edge in a simple graph is a cut edge if and only if that edge is not a part of any simple circuit in that graph. What is a simple circuit? As we discussed earlier, simple circuit is a circuit which starts and ends at the same vertex and no edge is repeated. Okay, so an edge is a simple graph is a cut edge if and only if that edge is not a part of any simple circuit in that graph. Okay, so this is another alternate definition of that cut edge. Okay, so or bridge. And then similarly, a vertex V is in a connected graph is a cut vertex if and only if there are vertices A and B both different from V, such that each path from A to B passes through V. Okay, so then this is another definition of cut vertex. So if you want to see whether a vertex is a cut vertex, you can check, you can take any two different vertices and see if each path from between those vertices pass through the vertex you are considering. Okay, now let's go to the example and see whether we can use this definitions or we can use these as definitions. Okay, now let's start with this guy. Now we have A here. Now A, if we remove A, we will end up with only this and this. Now still it is connected because you can reach any vertex from any other vertex. So A is not a cut vertex. What about B? B is the same. If we remove B, then we can go from A, C, D, E, F and E. So it is still connected. And similarly, because this is a symmetric kind of a graph, that E and F are the same. But what about C and D? If I remove C, for example, if I remove C, then A and B are connected and D, E, F are connected. But this part is not connected to this part. So C is a cut vertex. Same with D. Okay. Now let's see whether we can use something here or not. Okay, but before that, let's go to cut edge now. For cut edge, if we remove this one, then it is still connected. This is connected, this is connected, and then so on. And if we remove E2 or E3 or E5, E6 and E7, so you can easily see that the graph is still connected and now there's only one connected component. Note that this is a connected graph, so there's only one connected component. So if we remove this by this definition, we should have more than one connected component. Okay, so if we remove E5, E6 or E7 or E1, E2 or E3, then we will have still one connected component. But if we remove E4, then we will have two connected components, this triangle kind of a thing and this triangle kind of a thing. So then E4 is a bridge or a cut edge. But then let's use this guy. An edge is a simple graph is a cut edge if and only if that edge is not a part of any simple circuit. Now note that this is a circuit because it starts an edge with D. Now E4, E6, sorry, E5, E6 and E7 are part of this circuit, so they cannot be cut edges. Similarly, E1, E2, E3 are part of this circuit, so they cannot be cut edges. E4 is not a part of any simple circuit, so E4 is actually our cut edge. Okay, so these are my articulation points. So we can say cut vertices, and this is only my only cut edge. Okay, now let's go to this one. So now is A a cut vertex? If you remove A, we still have one connected component. Is B a cut vertex? If we remove B along with E1 and E2, then we have this part connected component, then this is an edge on its own and an edge on its own. Now the question is whether a graph which has just one edge a connected graph or not. So this is by theory it is still connected, because if this is a graph with only one vertex and you are here, you can still reach the only graph or the only vertex in the graph. Okay, so it is connected. By connected, we mean that there's a path from each vertex to a different vertex. So since there is no different vertex here from A, so then this means that this by convention. Okay, so sometimes it may be a little bit counterintuitive that if the graph with just one vertex without any edges, how is that connected? So if we go to back to the definition of connectivity says that there should be a path from each distinct pair of vertices in the graph. So there is no distinct pair here, so therefore we don't need to check any path. If we don't need to check any path, this is by default connected. Okay, so in this case we say that this is connected and this is connected, so then this means that B is a cut vertex. Similarly, C is a cut vertex, because if you remove C, then you remove along with E2, E3 and E4, then it's clear that this is a connected component and then this part is the connected component. Similarly, F. So if you remove F, then we remove E4, E5, E8 and E6 along with that. So if you remove F, you remove E4, E5, E8 and E6 along with that, and then you will see that this part will be connected, this part will be connected, and this part will be connected. So if we remove F, for example, so then you will see that you have this part and then you have this part and you have this part. So it's clearly one connected, second connected component and third connected component. Okay, and similarly G is one connected component. Why is I not a connected, not a cut vertex? If we remove G, then we still have two connected components. But if we remove I, we still have, along with E9, then we still have only one connected component. Okay. What about cut edges? So cut edges, only E5, E8 and E9 are not cut edges. Everything else is a cut vertex. So we have E1, E2, E3, E4, E6 and E9. Okay, so now how can I easily check it? Because these three are the only edges which are a part of any simple circuit here. Okay, so therefore they are not cut edges, and rest every one of them is a cut edge. Okay. Okay, so again, if you need to prove any of them, then you can assume induction, or you can assume any inspection kind of a thing. Um and we can prove it actually without much problems, just by assuming something. Or we can use contrapositive kind of a proof, or we can prove by contradiction. So there are many ways to prove this. So this is it about a simple example about cut vertices and cut edges, or articulation points and bridges. I hope it was easy to understand. And thanks for watching. Hope you liked the video.